Welcome everyone to Young Researchers Colloquium. Our speaker today is Alexander Frei, who will talk us about non-local games, synchronous and graph games. Please go ahead.
Thank you, Jacek. Thank you for the opportunity to speak in the Young Researchers Seminar. Thank you, Krzysztof. Hi, Krzysztof also.
Hi.
Nice to see you again. Yeah, so the idea about this talk is like to give you some nice introduction, like a teaser, like for this subject. And what's nice about this subject is that when you know some things, when you're like working in operator algebras, then you might find that non-local games is actually like a nice area where one can work with whatever, like you're basically from every side of operator algebra that you come from. You can do some nice, you can work out some nice results. Okay, so for this, let me first define what is a non-local game to give you like some idea. So non-local game consists of a referee, two players, Alice and Bob, and the referee asks questions for Alice and Bob, and Alice and Bob have to answer to these questions. So there are question sets X and Y and answer sets A and B, and the game is given by the rules for the game, and this is usually like phrased in terms of a rule function, but basically we can just think about it like given to a pair X of X and Y of questions and a pair of answers A and B, which such couples like would tell you that you win or you lose. So if Alice and Bob answer with A and B, given questions X and Y, and if this rule function then tells you it's zero, this couple, then it would be telling them that like Alice and Bob lost. They try to win this game together, and the way they do so is like they don't define it, they don't give answers like deterministically, but they do it rather probabilistically. The strategy is given by correlation. Basically, they define like for every input pair X and Y, and they have set before the game, they have decided upon a strategy. So there will be a correlation for every pair XY. They choose a distribution of what kind of answers they should answer. Like, for example, one half they would answer with A equals 1, B equals 2, and other kind of like A equals 2, B equals 3. They would answer with probability 1/3 and so on for fixed pair XY. So that's also like how you can read it now, like one one fixed pair XY, the probability that they answer for some pair AB is always between 0 and 1, and summing over all possible answers so that they would answer with any AB must be 1. So the sum over AB is 1. And now you define what is a winning strategy. So winning strategy is nothing but basically they would always answer with a winning pair couple. So if for some input output the rule function tells that they lose, then the probability for this couple of input and output should be 0. So this is by definition a winning strategy. By definition, winning strategy is for those input-output pairs where the rule function tells that they lose, the probability is 0 that they answer such. Okay, but now the idea is like this. Unfortunately, I can't draw anything. Is Alice and Bob, they sit in some places, for example, in the box, like I sit now, and Bob, so Alice sits, for example, in a box like this, and Bob sits in another box. And they have chosen a strategy before the game starts, but after but then they separate each other, and they're supposed to answer without knowing what Bob received. So Alice is supposed to answer without knowing what Bob received as a question, why, and without knowing what Bob answers with what answers, with with what he answers. So, so how does Alice, respectively Bob, choose on an answer like with probability? So, for example, Alice A, given she got the question X. So Alice receives X and answers with A, and Bob receives Y and answers with B. And the idea is that beforehand we had a correlation like this. There was no separation. But what we do now is basically we ask that they can decide in their boxes what A or what B to choose. And they do so by, we only allow particular strategies in those that are non-signaling, so that allows them to answer independently of the other claim. More precisely, if you take up the marginal probabilities, so you take one fixed pair of questions, X and Y, for Alice and Bob, and you sum up over all possible answers that Bob could have answered. So you sum over B. You obtain the marginal probability for Alice. So of what is the probability that Alice could answer. And but then this should not depend on the question that Bob received. So given Bob has answered with any B, so we sum up over B, and then the probability that Alice answers with A is a priori still depends on the both question pairs. So for both question received, so X and Y, but it should then not depend anymore on Y, but only on what Alice received. So this way she can extract, so basically you're saying that it's constant with respect to any Y. So this way she can extract a probability for how Alice should answer with A. And the same way Bob. Okay. To illustrate you, to give you some idea about what kind of games there could be and what kind of like strategies, let's start with a very simple example. So for example, the graph coloring game. I mean, like you know it probably from other areas, and it comes up here as well. So you start with a graph. That's part of the game. That's part of the game rules. You start with a graph G. Say, for example, with 3 vertices, 1, 2, and 3, and all of them connected. So 1 with 2, 2 with 3, and 3 with 1, and it's undirected. It's an undirected graph. It's an undirected graph. And they're supposed to assign colors, red and or blue, to these vertices 1, 2, and 3. And the question is, can you color this graph with some rules, under some rules? So first of all, what are the questions and what are the answers, the possible answers? As input and output, so the questions and answers, you just take for questions, you take for Alice as well as for Bob. You take the vertices. So Alice and Bob both receive a vertex. So Alice receives, for example, vertex 2, and Bob receives vertex 3, and then they're supposed to answer with red or blue, each of them. And then they should answer they should answer in such a way that the graph would become repetitive. So the rule function, so basically telling us when when they would lose, so under which answers they would lose. So what kind of answers they should never give probabilistically, is basically now telling, okay, you take if they incidentally receive the same vertex, so X and Y, for example, both receive the vertex 2 as a question, they should also both answer with the same color. And if they, if it happens that they received adjacent vertices, for example, 1 and 3. So for example, Alice received vertex 3 and Bob received vertex 1. So X equals 3 and Y equals 1. Then they should answer with different colors. So Alice could, for example, answer with red and Bob could answer with blue. But they should answer with 0 probability with same color. So this is also, so let me just put it now in this way. So I've put it as a condition, but basically what you can do is like you can, so how you get the rule function like formally is just you take these two conditions, to the first condition, you take and the second as well as the second condition, and you take the complement. And then you define lambda to be 0 on the complement and lambda to be 1 on the if this condition is violated, you take lambda of this such a pair x, y, a, b to be 0. And the same for the second rule. But it's not so enlightening. So it's often it's better like to phrase it as a condition. So these are in fact also the rules for general graph. Okay. Now this was so far the example of the game together with the rules. And now we would like to now I would like to just like show you like how such a strategy could look like. So still the same graph, still the same input and output set, so the same questions and answers. And an example strategy could be, yeah, now I can't like draw, but like, let me just like, okay, very nice. Okay. So think about it like this. The correlation PABXY. For simplicity, let's think about like such a correlation to be given as a product of two correlations, one for Alice, PAX, and one for Bob, QPY. And we have to define what the correlation for Alice would be and for Bob. So let's take, for example, for Alice. Oh, okay. So this could be, for example, like so for every x, so x equals 1. X equals 2, so the vertex 2, and x equals the vertex 3. For each of them, you get a probability distribution, PA given x. So let's say, so this is A, this is A, and this is A. So this is A being, for example, blue and red, blue and red, blue and red. And we could choose, for example, some interesting probability distribution. For example, like this. This one here. So I'm just drawing like some nonsensical function, but it's only relevant what they do at this point. So. And for example, something like this, for example. So the sum of these two, we could ask, for example, to be always 1. So the sum of this value plus the sum of this value could be, we could ask this to be 1, the same here. And the same for Bob. So this way you obtain like some example strategy. So you could, for example, say, well, if she receives vertex x equals 1, she answers with probability 1/2 with red and other probability 1/2 with blue. If she receives vertex 2, she would answer, for example, with 0 probability blue, but always with red. And if she receives vertex 3, she could answer, for example, with probability 1/3. Oops. 1/3 with blue and 2/3 with red. So, this could be such a distribution. Okay. Of course, you can see that you can't win this game classically, right? I mean, like you can't color such a graph. If you, for example, color 1 with red, 2 with, then you would have to color blue, and 3 you would have to color, you cannot color with red nor blue anymore. But you could still say, well, you would like to optimize what kind of, like, what is the best probability that you get out of. But I'm not going to go into this. So you see, like, you can play around with probabilities. You don't have to answer like with only zero, like either red or blue, but you could answer with some probability, 1/2. Okay. Yes. So now, so I've described you. So what we did now is actually we described already a special class of correlations. So remember that we had the non-signaling correlations. These were the general correlations that made sense, that we are able to, that Alice and Bob can receive questions and answer independently. But now we have seen also an example of a correlation where they really have their independent distributions, and this will be automatic non-signaling. So the idea of all these correlation classes are basically you ask the players to be separated in a possibly slightly better way than just being non-signaling. So being non-signaling was kind of like the absolute bare minimum for them to answer independently without knowing what the other received and answered. But we'd like to have a more, we would like to have an internal structure that separates these players. So let's first denote like such a correlation in a more suggestive way by saying this is P Alice, Bob. What I mean by that is basically you take your original P A B X Y, so A B given X Y on the right hand side, and you just collect them into players. They say A in A comma X, B comma Y, and you can now ask for a special kind of strategies better than just being non-signaling, and these are the local strategies. So basically what you ask is, you ask the correlation P of Alice, Bob, so question answer pair for Alice, question answer pair for Bob. You ask them such the correlation to be given by the product of a correlation for Alice and a correlation for Bob. And because these correlation, yes, Christoph?
Sorry, what is a Q here? What is a Q here?
Yes, so Q is just another correlation. So a probability distribution. So I should have denoted it more
okay,
to be more clear. I should have denoted like P sub index Alice, P sub index Bob. They together give P like the correlation. But abuse of notation, I like wrote P Alice and P for Alice and Q for Bob. So P and Q are now separate probability distributions for Alice, respectively for Bob. And they together, you take their product, and this you define to be the common correlation. Does it make sense?
Okay. Q of Bob means that Q is strategy for Bob, yeah?
Yes, correct.
The notion.
Yes.
Okay, notation, okay.
Yes. Sorry, can you repeat that? Just
Q of Bob means that Q is strategy for Bob.
Mm-hmm.
This is definition.
Mm-hmm.
It's just notation.
Just notation. Yeah.
Okay.
So it would be some Q B comma Y, or Q B given Y.
See.
So this one here, for example.
Okay.
You see? Maybe I should have called it P, Q, and then R. R is the correlation for them together, which you can write as a product. So imagine you have some correlation R, A, B, X given Y. And imagine you were able to write it as a product of two correlations for the players separate as a product.
Okay,
Yes?
thank you. Yeah, thank
Yes, happy to, yes. So, but these correlations, like the set of these correlations is, you can imagine, it's generally not a convex set. So what you do is like you take its convex hull as well, and you also close it off, because you can imagine that if you run some you can make some approximate things, like, I mean, like you have to take the closure, the topological closure inside the set of correlations.
So
Okay.
every local strategy is non-signaling, yes, but the converse doesn't need to hold.
Yes, exactly. Yes.
Okay.
So they're non-signaling strategies, and that's actually like that's yes. So that is the whole gist of Cyrilson's Cyrilson conjecture. Maybe you heard about it. You
Yes, a
can
little
generate.
bit, not much.
Yes, yes. So I will come to it in a moment, but basically every non-signaling strategy, every local strategy is a non-signaling strategy, because what we had to check, remember, we had to check that, let me maybe jump over it. So no, let me not jump over it. Okay, so you had to check that it's non-signaling. So if you sum up over B, then the remaining part will not depend on Y anymore. And if you sum up over A, then the remaining part will not depend on X anymore. So imagine this, you see this, the product here written with A and with A X's and B Y's. If you sum up over B now, and you have that the sum over B Q B Y is 1, then the dependency on Y drops out.
Yes, I agree.
And the same way, like if you sum up over A, then the sum over A PAX is 1. And so the dependency on X drops out. So that was this one here. The sum will be independent of X and Y, respectively. Okay. Yes. Now we have a small subclass, but it's not so relevant, but it's just like nice to know. There's a subclass of deterministic local strategies. So these are strategies that are given even by functions. So not that you have, like, for example, remember we had this that Alice could answer with 1/3 red and 2/3 with blue. But imagine she would, for every X, she would certainly give either like 0 probability for one of the colors and 100 probability to the other color. So it would be exactly like a deterministic strategy. It would be like saying that given any X, she tells exactly like, given any X, she tells exactly, so for example, X equals 2, she will answer with 100% probability with red. So that's just a function. Given X equals 3, she would not answer with 100% probability, but only unless like she would answer with 0 with blue and 100% with red. Okay. So that's exactly like you have a function that assigns for every X a precise color, like red or blue. And the same for Bob. So these are the deterministic strategies. Okay, now let's view a simple example for like where you can find a classical solution. So imagine you have, for example, like input output being both being a single bit for Alice and Bob. So Alice and Bob receive X and Y being either 0 or 1, and have to answer with A and B being either 0 or 1. And the rule function would be just like so, given by the condition that Alice has to answer with the sum of both bits that were sent out as a question, and Bob the same way. Both has to answer with the bit that is equal to the sum of both question bits that got sent out. Such a winning strategy would require that they can only answer with A, B given by the sum of x plus y. There's no other choice. So they have to answer this certainly with 1. And the probability that they have to answer with any other possibility must be 0 for being a winning strategy, because this is like, there is no way that they can answer any way differently. And now we can argue like this. So what one can do now is you can notice that what you're talking about here is like a convex optimization problem. And so that tells us that you can win classically, so locally, if and only if you can find which win deterministically, because the deterministic strategies, so the ones given by functions, turn out to be the boundary of the convex hull of the local strategies. So the boundary points of the convex set of local strategies are exactly the deterministic strategies. And so you can only win this possibly, like by this convex optimization problem, we can only win this if then you can also win it. If you can win it locally, then you can certainly also win it with a deterministic strategy. However, the latter is impossible. So if you were to choose, for example, so deterministic, meaning that I recall here, that the probability distribution for Alice is given by a function, and the same for Bob. Both functions f and g respectively, depending only on x for Alice and y for Bob. But in this case, this wouldn't be possible. So the function for Alice, so f of x, now I wrote it like as a of x, must be would need to be equal to the sum of both bits, and the same for Bob, but that's not possible. Like that depends on y as well. You can also make a nice exercise about it. Like you can, for example, play around with these, like for example, such probabilities, and see that if some of them must be 0, then you can run into a contradiction that they must also sum up to each of them must sum up to 1. So you can just like just a nice exercise. Okay, so we see that in real world, classical solutions are rather limited, or classical winning strategies. Instead, because they were simply too strict. If you think about it, like they asked your correlations to be given as a product, which is rather restricted. If you think about, for example, a matrix, like for each entry, they would be like telling you if one of them is 0, then each row and each column would be 0 for this entry. So this is like the drawback of having the correlation given as a product. Instead, we will now think about another way of separating, of having a better internal separation of the players. And so this is now the next bigger class of strategies, so which contains the classical strategies, but is still non-signaling. So it's still a subclass of the non-signaling correlations. It's now given by quantum commuting strategies. So for Alice and Bob, you have projection varied measures. So for Alice, you have projection varied measures, and for Bob, you have projection varied measures. What it means is you have, for each x for Alice, you have a set, a family EAXs. These are projections. So EAX squared is EAX is EAX star. So projections like in an operator algebra. And they are supposed to sum up to 1. So that would be the same as asking that the sum of probabilities is 1. And the same for Bob. So remember, X and Y are parameterizing pairs for the questions, and then A, B are the probabilities, the probability distribution. And you ask those, so you take such families. So the family EAXs. So this is one such family, and then for every X. This is for Alice. And the same for Bob. And then you just plug them in. So basically you ask P of AX BY is given by some state, some normalized state also now, phi in a Hilbert space, H, applied on EAX. So let me maybe write here, EAX FBY, and then compressed again from the right side, and then so compressed with a state phi. You would want those to be, and you would want the result to be positive values. So you want this to be positive. And so for this, we simply, what we do is like, generally we can't argue that like the product of two operators is a positive operator as well. But if we know that if we know that they commute, then we know that the product is a positive operator again. And so so we get the numerical values, these ones here, will be also positive. So knowing that this one, that they commute for every AX BY, implies that we get indeed positive values. Okay. Another thing. So these are the quantum commuting strategies. You allow EAXs to be projection operators on some possibly infinite dimensional Hilbert space. Sorry. Now, a slightly more narrowed down type of strategy are the quantum spatial strategies. So what you do now is you still keep projection value measures, but now you get the commuting condition. So the EF equals FE, so EAX FBY equals FBY EAX. You just incorporate it as by having the EAX is given as a factor for a product of for tensor product of Hilbert spaces. So EAX, these would be the EAX. Let me maybe like this. And FBY prime being one tensor. So if you have such operators that are given as unit, like as given block diagonal, and the other one like the other way around, like block diagonal, then you have them automatically commuting. And but you have them separated. You have them separate even spatially. So you in fact, this corresponds to I mean, like, so you could one can argue that the first type of strategies, the quantum commuting strategies, the more general ones. I'm not going to talk about this now. Okay, and with again some normalized state phi now in the tensor product. And if you take the closure, so the quantum spatial strategies are already define already a convex set, inside all correlations, but they're not necessarily closed in the set of all correlations. So we have to take their closure and define those to be the quantum approximate strategies. Okay, now we have a chain of inclusions. It's like this famous chain of inclusions. So you have the local strategies, then you have the quantum spatial strategies, you have the quantum approximate strategies. These are the closure of the quantum spatial strategies. You have the quantum commuting strategies, which are more general than the quantum spatial ones. They're already closed. So they are also contain the quantum approximate ones. So these ones here contain these ones here, obviously, but these are also closed. So they also contain these ones here. And finally, all of them are non-signaling. So all of them allow the players to answer separately, but they have the more internal separation. So you saw now that they're separated by, for example, by operators, either like commuting ones or possibly even spatial ones, like spatially as a tensor factors. And okay, so this is the chain of inclusions. So let me make a few remarks on it. So it has been like, as you might know or heard about, the quantum, it wasn't known for a long time whether the quantum spatial ones are already closed. So if you need to take their closure, it's not so obvious because if you remember the quantum spatial ones, you would allow for tensor products, or you allow for tensor products. And if you take a sequence of such strategies, so say Pn's with En's and Fn's and phi n's, it's not so clear. And if these correlations Pn converge to some correlation P, you might think that, well, maybe you could argue with some kind of like with some infinite and direct sum of those ENs and take them somewhat together, maybe take some ultra power and maybe still obtain like them separated as two factors, as two tensor factors. So it is not so clear if you need to take it, if you need to take also the closure. But it has, so, but like in 2000, not so long ago, I think in 2017 or 2018, and there was finally built up an example by William Slotstrom, who showed that like indeed these are not, so the quantum spatials are not closed off topologically.
Can I ask you for something?
Yes.
What
Yes,
do
please.
these dots mean?
Oh, in between there's also like yes, of course. So in between there's a more narrow class of quantum finite, as we call it, like quantum finite. So where you ask, so you can also argue, you can also think about the more smaller class of correlations, which are given like by finite dimensional operators E and F's. So EAXs and FBYs, so matrices.
Okay.
Yes?
Yes, okay.
Yes. So for example, you could think about like, maybe if you heard about like Pauli matrices, for example, you could maybe argue like, maybe come up with some nice combination of Pauli matrices that might give you some correlation, and then like, yeah. And so it turns out the closure of these two, both of them equal CQA. So the closures are identical. So here we have also CQS, sorry, QFin. So it's denoted Q usually, but let me write it as QFin. And you have that CQFin closure equals CQS closure equals CQA by definition. but then somebody found like that you can find a QS strategy that is different from QA strategy. Sorry, a QA strategy which is not so QA correlation which cannot be realized as a quantum spatial strategy. Okay, I'm gonna skip over these things. Like so, indeed, like verifying that if you sum over A, if you sum over B, okay, there may be this one, just this, that indeed all of them are non-signaling. So if you start with for example, if you start with a quantum commuting strategy, say, so given by EAX, FBY, the product of those, and then compressed with your state phi, you would like to know if these are indeed independent of, if you sum over B now, so for Bob's, what Bob has answered, that this becomes independent of Y. And so if we indeed sum up over B, we can pull in the sum. And the sum over B FBY was the identity by assumption of these correlations, of these types of correlations. And so we are left only with phi, the compression of phi on EAX, and which we now see is independent of what Bob has received Y as a question. So Alice can indeed answer independently of Bob. But I'm going to skip over why the local strategies are, why these, for example, these ones here, the PAX, QBY, why you can always realize them as quantum spatial ones. So you have to just believe me. And from here, if you are, I would like to give you a small teaser. Maybe like
I have a question before you go further.
Yes.
Is it so obvious that the set of quantum computing strategies is closed? I think you said it.
At first sight, no, I haven't said it. So at first sight, it's not so obvious. But what you can do, and this is like now where the operator algebras can shine. The set of quantum commuting strategies, in fact. So QC, you can think about it in this way. It was given by EAXs and FDYs in some B of H that commute.
Yes.
So what you can do is now you can now collect up the pairs AX and BYs as in a group. Slightly. So F and K is a group of Z, Zn, and then the free product Zk. Okay. Sorry, not Zn, but K many. Okay. Note the following. So if you were to take the group algebra, the the full group C-star algebra for Zn, that's nothing but the universal C-star algebra generated by at first by unitary of order n, but you know this corresponds to n many mutually orthogonal projections that sum up to 1.
Mm-hmm.
So a representation of the full group C-star algebra over Zn is nothing but a choice of EAXs, where you let A run, such that they sum up to 1. And if you do this now for every K many factors, so K is the number of X's, So this would be actually I think I can make this. So x, comma x1, and here you have a like this. And then so you knowing, so now because you have the free product, that's the same as just randomly choosing like such families with no further restrictions. So that's for Alice. For Bob, you can do the same. So let me call it shorthand F X A. So that's this this group, and the same for Bob. And now you can take their operator algebras. So C star of F X A, and the same for Bob. F Y B. And now you have to make it. Now you have to make a pick. So you have to, if you take their tensor product to be the maximal tensor product, then a representation of this maximal tensor product corresponds precisely to having a commuting pair of star homomorphisms from each factor. So a commuting pair of such projection varied measures. This would be exactly like that EAX commutes with FBYs.
Yes.
And now finally, if you take such a representation, and if you take a state on this Hilbert space, that's the same as taking a state directly on this maximal tensor product. This here is equal to CQC. Okay. By GNS construction, every state induces like a representation where with a vector state that agrees with the original state on the group in the maximal tensor product.
Okay.
But you already know that the state space is weak star closed. Sorry, is weakly closed. So it's like point quest closed. And so this way you obtain that CQC is already closed.
Oh, okay. That's. I guess I would need to check the details for myself. But
Yes.
I see some logic behind it, how it relates to these operators E, and that's very clever. I think.
Yes, indeed. It was a very nice insight that people got. Now, also, like you might wonder, like, well, say CQA is can be a somewhat strange player in this game of correlations, because we know that the quantum spatials, we know now that has been open now, which was open for a long time. We know now, just recently, that the quantum spatial ones are not closed, right? Even though one might think that one might come up with, for example, infinite direct sum or something like this. So generally, the only way, if you start off, like, you would first know only that CQA is just the closure of the correlations, and you would not know anything more, anything else. But it turns out that CQA is nothing but if you replace the maximal tensor product with the minimal tensor product. Sorry, with the spatial tensor product. So if you replace this maximal tensor product with the spatial tensor product, then this way you obtain the quantum approximate. So the closing off of the spatial strategies. The states on the spatial tensor product is exactly the closing off of the spatial strategies. It's exactly CQA.
But so now there is the spatial tensor product, which is the minimal one, yes?
Mm-hmm.
Okay.
Yes. So that's a nice thing to know. And from here on, I guess you can imagine if you come up with some obscure state, with a state obscure enough on this spatial tensor product, then this obscure state, if you take its GNS representation, might not be necessarily of the form as a tensor product. So if you come up with a state obscure enough, so not a state not given as a, so a state in here, you know, the states in here are the closure of the states phi times psi. Phi for the first vector, psi for the second vector. But if you come up with a state which is not of this form, just some general state, let's say chi, in here, then if you take the GNS construction, the GNS representation of this state, tensor minimal, like this, then it's not clear at all whether this fellow here can be written as some H tensor K, and such that this representation here is given by some, say, phi tensor psi or alpha tensor beta. You see the issue here, like.
Well, I can see that it's not clear that it can be written like this. I
Yes,
guess the other
and that's-
problem is to prove that it cannot be.
Yes, exactly. So you have to prove that it cannot be, and so for this you have to really find something. But you see that the line of problems,
Yes.
that it might not be spatial. Okay. So let me clear this. And let me give you a last quick. So do I have a little bit? How much time would I have more? Like how much time would be not too much taking of your?
Well, I guess you have 4 minutes, but I think you can go a little bit longer.
Mm-hmm. Okay.
That will not be a problem.
Okay, so I'll
It's
try
okay.
to keep it. It's okay. So just to give you a nice teaser, you know, like how really nice groups enter the stage. So now you're set up for tackling like these questions. Now let's see some maybe now let's see some nice example. Okay, I'm gonna make a stop share. I'm gonna share instead from here. Okay. So there's a nice class of games which are called the magic, or there's a nice game which is called the magic square game. And it's given like this. You have 3 rows and 3 columns of variables. Let's say 1, 2, 3, 4, 5, 6, 7, 8, and 9. And what you're meant to do is you're supposed to find binary to find bits, like binary input, binary values, 0 or 1, for these, and so on, such that they sum up to 0 here, they sum up to 0 here in this line, they sum up to 0 here in this line, they sum up to 0 in this row, however, that sum up to 1 in this row. And classically, you can't solve this this problem. Do you have an idea why so? Like assigning 0s and 1s to these fields, such that they sum up to 0s in each row and each column, except for the last row, column. Do you have a quick, nice idea?
Not immediately.
No,
Okay.
I can't see it.
No worries. Yeah, it's just I'm gonna spoil it. So please like close your ears if you don't want to. So you sum up all the variables all together. So 1 plus 2 plus you sum up every row and every column, and then you would end up with 0 equals the sum equals 1,
Yes.
which is a contradiction. However, we can solve it with a quantum spatial. I'm not sure it's spatial. At least we can solve it with a quantum strategy. And for this, what you do is you find now not just 0 ones, but you find symmetries. So self-adjoint unit trees that you can put in all these. So first of all, we translate these 0 ones into +1 -1s, and the sum into products. And then you find like self-adjoint unit trees. So their eigenvalues are either +1 or -1. You know, like something like this: s squared equals s star. Sorry, like this: s equals s star and s squared equals 1. So the like sigma, the spectrum of sigma, the eigenvalues are +1 -1. And you find examples of operators. So actually, even you find examples of matrices. And these are given like this: x tensor 1, 1 tensor x, and x tensor x. I'm going to tell in a moment what it is. 1 tensor z, z tensor 1, and z tensor z, as well as x tensor z, z tensor x, and y tensor. So x, y, and z, these are the Pauli 2x2 matrices. And because of their relations, you find out that if you multiply them together, so this with this with this, you end up x squared is z squared plus 1, the same for y. So you find out that this product here is 1 plus 1. The same way here, you find out that this product is plus 1, here plus 1, in these rows, columns, and in the last column you find yourself in -1. Okay. Now this defines a representation of the so-called solution group. Solution group is given by G, is given by the same generators. So these variables here, like C as a U1, U2, U3, U4, U5, U6, the abstract free group generated, together with commutation relations and so on, together with another J. This J is meant to represent the abstract -1. Okay, but you can't, there's no meaning of -1. Thank you. And then what you obtain is like, so what you obtain is basically you got a representation of this group. So this is the representation in B of H, which is here M2 tensor M2. And so you obtain also the representation of the free group of the universal group algebra generated by G. And finally, you also can check. So now you can check that J in this representation, J is distinct from 1. And this way you can construct a if you take the regular representation, which is also equal to the universal one, because the group is finite and so amenable. And in this regular representation, you can construct a state, which is given by this one here, this state, and then you plug in your abstract operators, so the GIs. And this way you obtain like this the self-adjoint unitaries. And now unraveling the self-adjoint unitaries into its spectral projections. So the eigenspace for the values plus and minus 1 respectively, you obtain the projection where it measures, so the EA axis and the FBYs. Oh, sorry, and you have to take here the left regular representation for Alice and the right regular representation for Bob. So this way you obtain commuting ones, and you end up with a so this gives you a quantum commuting strategy which satisfies the requirements. So this way you see how you very fast end up with some like groups and operator algebras, amenability representations, and so on and so forth. So this gives you like a nice, should give you like, hopefully gives you a nice teaser for this area. And yeah, how you can work. Yeah, thanks. Maybe I'll have, so thanks for listening.
Thank you very much.
Thank you.
Let me stop recording.